Welcome. In this case, we have a problem on cooling of a cake, another application of cooling problems. So when a cake is removed from an oven, its temperature is measured at 300 degrees Fahrenheit. 3 minutes later, its temperature is 200 degrees Fahrenheit. How long will it take for the cake to cool off to a room temperature of 70 degrees Fahrenheit? So this is an application of the Newton's law of cooling model. So solution. So this is an application of Newton's law of cooling. And Newton's law of cooling has the equation dt equals to k t minus ts. T at 0 is T naught, where T naught is the initial temperature and Ts is the temperature of the surrounding medium. So in this case, Ts is given as 70, so that the model will be dt is k into t minus 70. And then T naught is given as 300 degrees Fahrenheit. That's the initial temperature of the cake. So this is the problem now. And then after 3 minutes, the temperature is 200 degrees Fahrenheit. So T at 3 is given by 200. So remember our time in this case is minutes. So solving by method of separation variable, we'll have dt over t minus 70 equals to k dt. Integrating both sides, we'll have integral of dt t minus 70 equals to the integral of k dt, which will give us ln of t minus 70 equals to kt plus c, which means exponentiating both sides, we have t minus 70 equals to e raised power kt plus c, which is e raised power c, e raised power kt, and I can write this one as c1 e raised power kt, where c1 is e raised power c. So I have t minus 70 equals to c1 e raised power kt. But then we know that when t equals to 0, so remember this is the same thing as saying t of t, take this to the right, will be 7t plus c1 e raised power kt. When t equals to 0, then t is 300. So we'll have 300 equals to 70 plus c1 e raised power k times 0. So which is 70 plus c1. So this means that C1 equals to 300 minus 70, and 300 minus 70, we get 230. So then we have T of T is 70 plus 230 e raised power k T. Now, next thing that you are remaining with is to find K. Also, when T is 3, T is 200. So we'll have 200 equals to 70 plus 230 e raised power T is 3, so 3K. So 200 minus 70, we get 130. So 130 equals to 230 e raised power 3K. So which means that e raised power 3K equals to 130 over 230, which is 13 over 23. So e raised power 3K equals to 13 over 23, which means introducing ln on both sides, 3K equals to ln of 13 over 23. So which is K is a third ln of 13 over 23, which is equals to a third into ln of 13 minus ln of 23. So ln of 13 minus ln of 23 divided by 3 gives K equals to negative 0.190181619. So therefore, our model T of T will be 70 plus 230 e raised power negative, so roughly negative 0.19018. Zero point 19018 T. So the time needed to take this cake to have a temperature of 70 degrees. So T of T equals to 70 since limit as T approaches infinity of T is what is giving 70. So therefore, the answer to the given problem is 70 degree, is T should be infinity. And then another problem, a pie number 2 is removed from a 350 degrees Fahrenheit oven and placed to cool in a room temperature, in a room with temperature 75 degrees Fahrenheit. In 15 minutes, the pie has a temperature of 150 degrees Fahrenheit. determine the time required to cool the pie to a temperature of 80 degrees Fahrenheit. That's another application of Newton's law of cooling. So in this case, we know that the model that defines this situation is dt equals to k into t minus ts. T of 0 is T naught. So Ts is the surrounding temperature or the room temperature. So here Ts is given by 75 degrees Fahrenheit. And then the starting temperature is 350 degrees Fahrenheit. So this is what defines T naught. So the problem will be dt equals to K T minus 75 subject to T at 0 equals to 350. Now, by separation of variables, dt over t minus 75 equals to k dt. So integrating, we get which will give us ln of t minus 75 equals to k t plus c. So exponentiating both sides, we have t minus 75 equals to e raised power kt plus c, which is e raised power c, e raised power kt, which is c1 e raised power kt. So remember c1 is e raised power c, just another constant. So that is t is 75 plus c1 e raised power k t, or same thing as saying t of t equals to 75 plus c1 e raised power k t. Now, we know that t at 0 is given by 350. So then 350 will be equals to 75 plus c1 e raised power k times 0, which is 75 plus c1. And solving c1 will give us 350 minus 75, which gives 275. So then the model becomes t of t equals to 75 plus 275 e raised power k t. So the next step is to get the value of this constant k, but then also t of 15, after 15 minutes, the temperature is 150. So which means 150 is equals to 75 plus 275 e raised power 15k. So this means 275 e raised power 15k equals to 150 minus 75, which is 75. So this tells us that e raised power 15k equals to 75 over 275, which is 3 over 11. So introducing ln on both sides, we'll have 15k equals to ln of 3 over 11. So which means k is 1 over 15, ln of 3 over 11, which is 1 over 15, into ln of 3 minus ln of 11. Ln of 3 minus ln of 11 divide 15. Negative. So we get this one to be k equals to negative 0.086618865. So therefore, our T of t will be given by the model is 75 plus 275. E raised power negative 0.0866, say 19 T. So we're interested in finding the time required to cool the pie to a temperature of 80 degrees Fahrenheit. So when T of t is 80, what is T? So I'll have 80 equals to 75 plus 275 e raised power negative 0.086619 T. So 80 minus 75 you get 5. So e raised power minus 0.086619 T equals to 5 over 275. So 5 divided 275 is 1 over 55. So introducing ln on both sides, we'll have negative 0.08661 t equals to ln of 1 over 55. So t equals to, now ln of 1 over 55 is the same as ln of 1 minus ln of 55, which is negative 4.0073333185 divided by negative 0.086619. And this will give us T equals to 46.2639048. Approximately, this is approximately 46 minutes. So thus the pie will reach a temperature of 80 degrees Fahrenheit after about 46 minutes. That's how we solve that question. Thank you.